So we've done a lot of working with exponential and logarithmic functions, equations, properties, rules, you name it. We're going to pull it all together here. And we're going to talk about exponential and logarithmic equations. Excuse me. We want to solve both exponential and logarithmic equations. We've already seen some work on this one, logarithmic. But we also want to include some application problems as we work through this one. Okay, and we know a lot. All these pieces are in our toolkit, and they can all help us. We have to, pull from our toolkit various pieces in order to solve these equations or these application problems. So we know that the exponential equation and the logarithmic equation are inverse functions. This one undoes this one undoes this one. So if we're here and we need to find the exponent, we can rewrite it in its logarithmic form. If we're here and we need to find the argument or the base, normally the argument, we can rewrite it in its exponential form. We know the property of equality of exponents. In other words, if b to the x equals b to the y, if the bases are the same, then the exponents are the same. And it says it down here in a little smaller writing. If the bases are equal, the exponents are equal. We'll see an example of that. And we know these properties of logs: product property, quotient property, power property, and equality property. Okay, equality property. And we usually use the vice versa method. We usually go from here to here as opposed to here to here. Okay, so how do we solve these exponential equations algebraically? Well, one way to do it, if you see it, and if it's possible, is you can apply the property of equality of exponents, which is the first thing here. Assuming you can rewrite it with the same base. We'll do an example of that. Second way, you can rewrite it in your logarithmic form. Okay, you can be here, and write it as this to get there. And the third, you can apply the equality property of logarithms to solve exponential equations sometimes. How do we solve logarithmic equations algebraically? Well, we did this in a previous video. You can either rewrite them in their exponential form, which is up here. If you've got the log on one side and a non-log on the other, you can rewrite it in its exponential form, or you can apply the equality property of logarithms. If you have a log on both sides, one log on either side, you can do that. So let's get started. We'll do a variety of these things, and we'll pull in, I shift it up a little bit, we'll pull in various pieces of what we have up here and how they come into play with different problems. And of course, there are a number of ways to do things. You can solve problems in different ways. I'm just kind of showing you some examples of a variety of some of the different ways, and I'm showing you one way to do them. A few of these problems can be done in more than one way, of course, which is typical of mathematics. So example 1, let's solve 5 raised to the x minus 1 power equals 0.07. Well, we have a variable in our exponents. So we have this, 5 to the x minus 1. Let's make my minus a little clearer. Equals 0.07. And in here, we need to find an exponent. We have an unknown in our exponent. Well, that's what the log does for us. If I go up to here again, and the very first one I have up here, the log gives us the exponent. So I can rewrite this in this log form. Let's take this one and say, well, I know the log will get the exponent. So the log base 5 of 0.07 will give me the exponent, x minus 1, because that's what logs do. logs give you output, logs give you an exponent. I'll add 1 to both sides, and we'll come up with x is equal to the log base 5 of 0.07 minus 1. I will then pull out my calculator. I'll let you do that, and it's approximately negative 0.65. Can we check it? Sure. 5 raised to the negative 0.65 minus 1, does it give me 0.07? You can check that. Okay, let's keep going with some examples. It's nice to see a few. I've got a few lined up for you with some different pieces to them to show you some different ways of doing things. Okay, let's do this one. Okay, so this one says we want to solve 8 to the x equals 4 to the x squared minus 1. Well, I've got these I've got these unknown exponents on both sides. However, I'm going to make use of the equality property of exponents. Let's recognize that 8 is equal to 2 cubed. I know my powers of 2 pretty well. And 4 is equal to 2 squared. So I can replace 8. Okay, so I can replace 8, right? I can replace 8 with 2 cubed. And I can replace 4 with 2 squared. Okay, so this is 8, and this is 4, just replaced with their exponential equivalencies. Now notice I have the same base, but I can't use it yet because I've got power to power. Remember your exponential rules, a number to a power, you multiply the powers. So this is 2 to the 3x. I'll multiply these powers, which requires the distributive property. This is 2 to the 2x squared minus 2. This 2 gets distributed. Now I have same base, which means the exponents are equal. Here is the exponential equality property. Okay, right there. So I know 3 squared is equal to 2x squared minus 2. Okay, this is the equality property of exponents. Now this one took a little bit of knowledge of exponents. I had to know that 8 was 2 cubed, 4 is 2 squared, so I had the same base. I had to know the exponent raised to a power rule, and then the equality property. So that took a bit of exponential knowledge. Well, I see a quadratic, so let's set it equal to 0. So 2x squared minus 3x minus 2 equals 0. And this one's factorable as it turns out, or you could use the quadratic formula. Let's see, I think I factor it this way with a minus 2 and I think a plus 1. Let's see, that's 2x squared minus 4x plus x is minus 3x minus 2. So in this case, x equals negative 1/2 or x equals 2. And you can check your answer. I think they both work. You can check your answer using a calculator, okay? So check using a calculator. Let's write that down. Check answer. Always check your answers when you come up with, always check your answers when you have these things. Let me plug in my phone. Looks like my phone is running out of power, so let's plug it in. And that might get me back to where I need to be. Okay. Let's take a look at, just a second, I gotta do a little bit of work here. Whoops, all right, that might get me where I need to be. Think so, okay. Example number 3. Let's solve this logarithm. Now notice I have a single log on the left, and I wanna get at the argument. So this seems to suggest if I can get this to be a single log, I can rewrite this using the exponential form. I can use the inverse function to get at it. So let's first move this 5 using the power rule. Okay, so this would be log base 6 of 7x plus 1 to the 5th power is equal to 10. And this is the power rule. We've used that previously. Okay, now I've got a single log equals a number or something on the left. I can now use the inverse function, the exponential function, to get at it. Okay, so I'm going to rewrite this as 6 to the 10th power is equal to 7x plus 1 to the 5th power. Okay, so I am using the inverse operation. I'm using the exponential form to get at it. Okay, I'm getting at the argument this way. Now, 6 to the 10th power, huge number. I put it in my calculator and I got 604,66176. Hope that's right. And that's equal to 7x plus 1 to the 5th. Now I can take the 5th root of both sides. And I have 7x plus 1. It turns out the 5th root of this is 36. That worked out nicely. This is 36 to the 5th power is this big number here. And of course now I can subtract 1 from both sides and I get 7x equals 35. This looks like a math book problem because they made it work. Divide both sides by 7 and I have x equals 5. And again, check it with your calculator. You can all quickly check that 5 times 7 is 35 plus 1. So my argument is positive, that's fine. But I would put this in a calculator with 5 going into here to see if the answer comes out to be 10. So here we use the power rule and we use the inverse form to get at the argument in this case. Okay, let's keep going. Let's get some more in here. This does take a little bit of practice. Give me a second to get my notes together. Okay, let's take a look at this one. Solve the natural log of 2x minus 1 minus 2 times the natural log of 4 equals 3 times the natural log of 2. Okay, well this one suggests, as I look at it, that I have natural logs on both sides. If I can get these two combined, then I can use the equality property of logs and I can drop the natural logs. But first, I need to do a move here and I need to combine these two. So let's first let's do one step at a time. Let's use the power rule on the right side. So I'm leaving the left side alone. I know I can do this. I know I could do this. Whoops. Oh, hang on a second. I just forgot something. There's also a number in front here. So I can do two things at once. I can move this multiplier to a power. And I can move this multiplier to a power, assuming I can do it correctly. And this is the natural log of 2 cubed. So here I made use of the power rule. Okay, so now I can simplify these two. I know these values. 4 squared is 16. 2 cubed is 8. So let's just simplify those. That'll be my next step here. The natural log of 16 equals the natural log of 8. That was just some simplification there with the exponents. Left side is nice and simple. I have a single natural log. Right side is nice and simple. I have a single natural log on the right. And I have a log minus a log on the left. So let's use the quotient rule. This is the natural log of the numerator divided by the denominator, or the first is the numerator, the second is the denominator, and I'll simply copy the right side, and this is the quotient rule. Well, wonderful. Single log on left, single log on right. I can drop the logs using the equality rule. So 2x minus 1 over 16 is equal to 8. And this is the equality rule. My R's are looking funny here. Now let's just do some math. Multiply both sides by 16. And I have 2x minus 1 is equal to 128, I hope, with my calculator. Add 1. 2x is equal to 129. Divide by 2. X is equal to 129 over 2. And that's my answer. Okay, again, you're going to want to check it with your calculator. It's an equation you can check. So check with calculator to see if you're right. As I tell students, you never ask your teacher, am I right? Because you can check it, okay? If you check it and it works, you know you're right. If you check it and it doesn't work, you then can ask your teacher, I know my answer is not correct, but I can't find my mistake. Can you help me find my mistake? Okay? Asking, am I right, makes no sense because you can see if you're right or not by putting this into a calculator up here and checking it. Okay, another example. I got a few more. We'll do some application stuff here. Okay, according to one model, the number N of Americans in millions age 65 and older that will have Alzheimer's disease T years after 2015 is given by this exponential function. N equals 5.1 times 1.03 to the t power. In what year will this number reach 8 million? We want to have N be 8 million. So here's our function. The number of Americans with Alzheimer's in millions equals 5.1 times 1.03 to the t. In what year, at what time will we have 8 million? So we'll put 8 million in for N. And I want to solve this for t. So I've got this exponential thing. I've got an unknown in my exponent. And so I'm going to have to use logarithms to get at this. Well, first things first, let's divide both sides by 5.1 so I can get that 5.1 out of the way. And I'm going to leave as a fraction. I'm going to leave it as a fraction for right now. Okay, that's okay. Let's leave it like this. So leave it as a fraction. Now I have base to exponent equals a number. And so I need to find the exponent. Okay, which means I can rewrite this as a log. Okay, so let's see here. Base, so log base 1.03 of 8 divided by 5.1. The log equals the exponent. Okay, so rewrote it as the inverse, which is the log function. Remember, the log gets to the exponent. This is the base, this is the argument. Well, this can go into a calculator just as is, and t is going to be 15.23 years after, because t is the years after 2015. So in what year? Well, we got to add 2015 plus 15.23. So the answer is approximately in what year? In the year 2030, approximately. And we solved this one to figure that out. This one was an exponential, and we had to use logs to get at that exponent, which allowed us to come up with the answer. Okay, let's keep going. I got two more real life or application problems. And we've seen one of these before when we worked with compound interest in a video some lectures ago. Okay, so the compound interest formula, when it's not continuous, is A is equal to P times 1 plus R over N to the NT. And this describes the final value, the ending value A, also called the accumulated value, of a sum of money. So you put P in, that's the amount you deposited, after T years, at an annual percentage rate of R, which is written in decimal form, compounded N times per year. How long will it take $50,000 to grow to $1 million if we're going to compound annually at 9%? If we have a rate of 9% compounded monthly. Okay, we know that 9% in a decimal is 0.09. That's our R. So our final amount is equal to our starting amount times 1 plus R over N to the NT. We want a final amount of $1 million. So let's get 6 zeros in there. We're starting off with 50,000, not nearly as much. 1 plus our rate is 0.09. We're compounding monthly, which means our N is 12, and that's 12 times T. And you should be thinking right away, I've got a variable in my exponent. I'm going to probably make use of logarithms to get at that exponent. So let's first divide both sides by 50,000. On the left, I have 20. 20 equals, I'll do this math here, okay, just to I can kind of get that out of the way. I'll do this math. It's equal to 1.0075, so that's what 1 plus 0.09 divided by 12 is, raised to the 12t. Okay, so again, I need to get at the exponent. So let's rewrite it using the inverse function, the log function, base, exponent, argument. Okay, so I have a log. The base is kind of funky. It's going to be 1.0075, but our calculator can handle that. Our argument is 20, and that's taking the log will give me the exponent, which is 12 times t. So we've written it as the inverse. We've made use of the inverse function, which is the log function, to get at the exponent. Let's divide both sides by 12. So t is equal to this big mess, log base 1.0075 of 20 divided by 12. And the answer in time is approximately 33 years. So if you're young and you can find something that's giving you a 9% rate compounded monthly, and you deposit $50,000 in 33 years, you're gonna have $1 million. Not bad. That's the power of compounding. Compounding, a whole other topic in finance. Last example, I think we're gonna go back to logs in this one and use a little natural log. Let me get this up high enough for us. Okay, medical research indicates that the risk of having a car accident increases exponentially as that should be a T right there, as the concentration of alcohol in the blood increases. The risk can be modeled by this exponential equation or this exponential function, R, which is the risk as a percent, equals 6 times E raised to the 12.77 times X, where X is the blood alcohol concentration. Okay, so what blood alcohol concentration corresponds to a 17% risk of a car accident? Okay, well, we know this. R is equal to 6 times e to the 12.77 times x. So let's plug in. We know that R is 17. Because we want to have a 17, we want to see a 17% increase, a 17% risk, and R is given as a percent, so it's 17. 6 times e to the 12.77x. We're here. And again, here, we need to find or to get at the exponent. We're solving for an exponent, so let's use the log and rewrite it. Now, it's base e, so let's use the natural log, okay? So I'm going to rewrite this with natural log. Whoops, I made a mistake. Let me step back. I can't do that yet. I'm looking at my notes and I'm seeing that I made a quick mistake. Okay, sorry about that. I first need to move the 6 over. Divide both sides by 6. So 17 over 6. I gotta have the exponent part all by itself. Okay, now I can do what I said. Now I need to find the exponent. Sorry about that. I need to find the exponent. So I've got it where there's nothing else in front. So now I can rewrite it. Base, exponent, argument. And since it's a base of e, I can just say the natural log. Okay, so the natural log is e. The natural log of 17 over 6 is equal to the exponent, 12.77 times x. Okay, so this is the inverse, and I used the log, which I used, I'll kind of put a slash here, I used a natural log. If you want, put a little e down here. E to the exponent equals argument. This was the exponential form. I rewrote it in its inverse form, in its logarithmic form. To get x, just divide both sides by 12.77. And I have the natural log of 17 over 6 divided by 12.77. That goes into a calculator, and out comes approximately 0.08. So in other words, what blood alcohol concentration, so a BAC, which is how it's abbreviated, a BAC of 0.08 corresponds to a 17% risk of a car accident. Check it. You should be able to put in 0.08 into here, and you should be able to get 17 coming out of here. So, a lot of different problems, including some application problems. Working with logs takes time and knowledge of those exponential rules or properties and those logarithmic rules or properties.